Our first lesson is going to be about right triangle trigonometry. Now, a lot of times when we just say trigonometry, we're often referring to right triangle trigonometry. But since in the next few chapters, we're going to be focusing solely on trigonometry, we need to be specific. Sometimes we're talking about right triangle trigonometry. Sometimes we're talking about more generic types or oblique triangle trigonometry. It does not have to be a right triangle for trigonometry to apply, although within the entire chapter 4, yes, we will be exclusively sticking with right triangle trigonometry. As soon as we get to chapter 5, though, right triangles are out the window. In this lesson, our learning goal is to be able to give a trig ratio based on either a given triangle or from another trig ratio. If I give you a sine ratio, tell me what the cosine ratio is. We also want to be able to solve right triangles. If I give you a right triangle and any other two pieces of information, either two sides or an angle and a side, I should be able to find any other relevant piece of that right triangle. And we're going to use that concept of solving right triangles to help apply trigonometry to solving application problems. If I'm climbing up a tree, how long is the shadow? If the angle is this or that, or so on. So, speaking of trigonometric ratios, there are 6 of them. There is the sine, cosine, tangent, cosecant, secant, and cotangent ratios. In geometry, you probably only learned about the first 3, sine, cosine, and tangent. You probably learned that the sine ratio is the ratio of the opposite side of an angle to its hypotenuse. Cosine is the adjacent side to the hypotenuse. Tangent is opposite to adjacent. Cosecant, secant, and cotangent are typically saved for later courses. We don't typically go over these in a geometry course. We just stick with the main 3. Cosecant, secant, and cotangent, though, are just as easy. They're basically the original 3 flipped upside down. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. In other words, cosecant is just sine upside down. Secant is cosine upside down. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. Tangent is opposite over adjacent. Cotangent is adjacent over opposite. Now, a couple of these vocab words, tangent and secant, hopefully should be familiar to you. When we talked about circles way back in your geometry course, a tangent or a tangent line is a line that touches a circle only once. A secant is a line that touches a circle exactly twice. And for that matter, a sine is not a word that you covered in geometry, although you did cover a different word, a chord. A chord has endpoints on the circle. Now, the funny thing about translations between different languages, the word sine began its life in the Sanskrit language as the word jiva, J-I-V-A. I have no idea if I'm pronouncing it correctly. I'm just going to say jiva. And it meant chord, the chord of a circle. Now, when it was translated into Arabic, it became jiba, J-I-B-A. And it still meant chord. But when it was translated from Arabic to Latin, whoever translated it misread the word because jiba was abbreviated JB, just like we abbreviate sine, S-I-N. So because the word was being abbreviated JB, they misread it as the word jaib, J-A-I-B, instead of J-I-B-A. And that word meant something completely different. It meant bay, like a body of water. So when they translated it into Latin, it became the word sinus, which means the same thing. Just like you have sinuses in your head, which are like tunnels in your skull that connect this and that and whatever. But the word sinus, which meant bay, became our word sine, which means the opposite side of a triangle to its hypotenuse. But in its infancy actually had a geometric meaning, chord. Now these other 3 guys, cosecant, cosine, and cotangent, co is actually an abbreviation of complement. A cosine is the complement of sine. A cosecant is the complement of secant. Cotangent is the complement of tangent. Complement in geometry meaning 2 angles that add to 90 degrees. So if I take the sine angle and the cosine angle and add them together, it will always equal 90 degrees. Of course, if it's a right triangle, one angle already equals 90 degrees, and the 2 acute angles together add to 90 degrees. Well, those 2 acute angles represent the sine and the cosine. Now, for some more formal definitions of those trig functions, as well as their appropriate notations, stuff you should already know. Sine is abbreviated S-I-N. Sine of this letter right here, that is the Greek letter theta. We use the letter theta to represent angles. Just one of those common things we use in mathematics. Get used to it. If you don't like it, tough. So if theta is this angle down here, sine is defined to be the opposite over the hypotenuse. So then we can say that sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, so we'd write cos of theta equals adjacent over hypotenuse. And of course, tangent of theta, that's the opposite over the adjacent, so opposite over adjacent, just like that. As I said before, we had three other trig functions, secant, cosecant, and cotangent. Sine and cosecant were the ones that were upside down from each other. So if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. Cosine becomes secant, adjacent over hypotenuse flips upside down. We have hypotenuse over adjacent. Tangent and cotangent are the flips of each other. Opposite over adjacent becomes adjacent over opposite. Now remember, when you were in geometry, you were probably taught a handy-dandy little trick to remember the sine, cosine, and tangent ratios. SOHCAHTOA, S-O-H-C-A-H-T-O-A, SOHCAHTOA. SOHCAHTOA is an easy little mnemonic device to help you memorize that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. SOHCAHTOA. Unfortunately, we don't have that as memorable as a mnemonic device for cosecant, secant, and cotangent. I've attempted to come up with one, CHO-SHAKOW, but I don't think it really works all that well. The way I remember things is I remember that no two cofunctions go together, so it's not cosecant and cosine, it's cosecant and sine. For that matter, I can't put sine and secant together because you have to have at least one cofunction in each. Sine and cosecant go together, cosine and secant go together, and it's usually super easy to remember that tangent and cotangent go together. So as long as you remember sine, cosine, and tangent using SOHCAHTOA, with a little bit of work and a little bit of studying, you can memorize cosecant, secant, and cotangent as well. Now I keep using that word flip. Sine is the flip of cosecant, cosine is the flip of secant, and the same for tangent and cotangent. But of course, flip is not a math word. We have another word when we want to flip something over. And of course, that's reciprocal. So since I know that sine and cosecant are defined as reciprocals of each other, sine is opposite over hypotenuse, cosecant is hypotenuse over opposite, then we can simply say that sine is equal to 1 over cosecant. In other words, sine and cosecant are reciprocals of each other. This right here is referred to as a reciprocal identity. In other words, an identity is a statement that's always true no matter what value I pick for theta, no matter what angle I plug in, sine is always going to be 1 over cosecant. And for that matter, cosecant is always 1 over sine. And since we have 4 more trig functions, we can identify 4 more reciprocal identities. Cosine is 1 over secant, secant is 1 over cosine, tangent is 1 over cotangent, cotangent is 1 over tangent. So as we're going through in this lesson and we start trying to figure out what certain trig ratios are, if I tell you that the sine ratio is 3 over 5, simply by knowing my reciprocal identity, if sine is 3 over 5, cosecant would have to be 5 over 3, because sine and cosecant are reciprocals of each other. If cotangent is 1/2, then tangent has to be 2. They're reciprocals of each other. Now these are not the only identities that we're going to have in trigonometry, not to worry you too much, but by the end of chapter 5, there are going to be 23 fundamental trigonometric identities that I'm going to ask you to memorize. So these are 6 of them. You might as well start memorizing them now. The earlier you start memorizing these identities, the easier trigonometry is going to be to you. It's just like the earlier you learn how to count, the easier arithmetic is for you. I call these identities fundamental identities because they are so incredibly useful. That's why I want you to memorize them. They come up, the necessity for them comes up so often. You don't want to have to say, oh, I think there's a rule for that, let me go look it up. It should be, oh, this is the rule for that, let's apply it and move on. So the reciprocal identities, these are the first 6 of the fundamental identities that you're going to need to memorize. And of course, it's not even 6 rules that you have to memorize. As long as you remember that sine and cosecant are reciprocals of each other, There are two identities you've got by simply memorizing one concept. Sine and cosecant are reciprocals. And if sine and cosecant are reciprocals, then cosine and secant must be reciprocals as well. So really there's 4 in 1. And then of course tangent and cotangent, you just got to remember that those go together. So by memorizing just a couple of things, you've got all 6 of these identities at your fingertips. Now a couple more identities that we're going to need to know. Sometimes you can refer to them as the quotient identities, other times the tangent identities. I really don't care what you want to call them. I just need you to know what they are. And it has to do with what happens when I divide sine by cosine. Well, I know that sine is defined to be opposite over hypotenuse, and I know that cosine is defined to be adjacent over hypotenuse. And when I'm dividing fractions like this, if I have 3 over 2 divided by 1 over 2, the fractions, the denominators of the fractions would cancel out. So I'd just be left with opposite over adjacent in this case. Well, wait a second, opposite over adjacent, isn't that something else? Yeah, that's tangent. In other words, tangent is equivalent to sine over cosine. There is our first tangent identity, or quotient identity if you want to call it. Of course, we call it a quotient identity because it's a quotient. Tangent can be replaced with sine over cosine. And for that matter, since tangent and cotangent are reciprocals of each other, looking back at the previous set of identities, if tangent is sine over cosine, then cotangent must be cosine over sine. Tangent and cotangent are reciprocals, so simply take their rules and flip them over. So here are your 2 tangent identities. So out of the 23 fundamental identities that I'm eventually going to have you memorize, we now have 8 of them done. So start memorizing the trig identities now. There are more to come. We've got a lot to do in this chapter and the next chapter, and you don't want to wait until the day before the test to start memorizing them because you're going to have no idea what's going on in the next 2 lessons because they're going to be based on those trig identities over and over and over again. If I can make a suggestion, flashcards are a fantastic tool. Again, there's going to be a lot to memorize in this chapter. Make some flashcards, with the identity on one side, sine over cosine on one side, on the other side would be tangent, with 1 over cosecant on one side, the other side would be sine. So start memorizing those identities as quick as possible. So one more quick refresher before we jump into anything, and that's the Pythagorean theorem. Of course, the Pythagorean theorem says that for any right triangle, the sum of the square of the 2 legs is equal to the square of the hypotenuse. A squared plus b squared equals c squared. Now it's going to often be the case where I'll give you 2 sides of the triangle and you're going to need to know the third side, and we can simply find the third side by using that Pythagorean theorem. I just think it's a little bit of a waste of time to write things out. It's much quicker to just kind of memorize when you should add and when you subtract. If I give you the 2 legs and ask you for the hypotenuse, sure, I could write out a squared plus b squared equals c squared, plug in a and b and solve for c. But if I give you the 2 legs, I know I'm going to have to square a, I know I'm going to have to square b, I know I'm going to have to add these together, and I know I'm going to have to square root c squared to get c by itself. So why not simply memorize the formula as c equals square root of a squared plus b squared? A little bit quicker, I think. So if you're given the 2 legs, simply square, add, and root, and there's your hypotenuse. For that matter, if you're given a hypotenuse and one of the legs, you're not going to add to figure out the missing leg, you're going to subtract to figure out the missing leg, always subtracting from the hypotenuse. Because of course the hypotenuse is always the bigger number, and you want a square root, you want the number underneath the square root to be positive, so you always have to lead with the bigger number. So again, not necessary to memorize these formats of the Pythagorean theorem. I just think it's a whole lot quicker to think of it like this instead of that standard a squared plus b squared equals c squared. Speaking of a whole lot quicker, something about Pythagorean triples. If you don't remember anything about Pythagorean triples, I encourage you to simply look up a YouTube video. Search term would just be Pythagorean triple. A Pythagorean triple is simply a set of 3 numbers that satisfies the Pythagorean theorem. Now, of course, not any set of 3 whole numbers satisfies the Pythagorean theorem. If I tried to plug in 1, 2, and 3 into a squared plus b squared equals c squared, it's just not going to work. But 3, 4, 5 absolutely does work. And 3, 4, 5, it's such a nice, neat set of numbers, 3, 4, and 5, they come up a lot. So instead of constantly having to use the Pythagorean theorem to figure out, well, if the 2 legs are 3 and 4, what's the hypotenuse? Just get used to knowing that if the 2 legs are 3 and 4, the hypotenuse is 5. It's not like it's going to change between today and tomorrow, and since it's going to come up often enough, just memorize it. 3, 4, 5. And for that matter, if you know that 3, 4, 5 is always going to work, 6, 8, 10 is also going to work, because that's simply 3, 4, 5 times 2. So get used to seeing multiples of certain Pythagorean triples. So 3, 4, 5, that's going to be one that's probably going to come up the most often because it has the smallest numbers. It's the smallest Pythagorean triple that you can have. Now, there are an infinite set of Pythagorean triples. There's a fancy little formula. As long as you pick any random number, plug it into the formula, it'll pop out a Pythagorean triple that if you're curious about, you're more than welcome to research it on your own. But there's only a few that you really need to know, and basically it comes down to the ones that I have memorized, you should have memorized, because if I have them memorized, then they're going on the test. And if they're going on the test, you might as well memorize them. In other words, these are triples that you should not have to grab a calculator for. If I see legs of 5 and 12, the hypotenuse is 13, automatically, because it's a Pythagorean triple. If I see 8 and 15, I know the third side is 17. If I see 7 and 24, I know the third side is 25. So those 4 Pythagorean triples, I highly recommend that you memorize, and you're more than welcome to prove them to me. If I say 3 squared plus 4 squared, does it equal 5 squared? If I say 8 squared plus 15 squared, does it equal 17 squared? Now keep in mind, there's still rules about right triangles. The third number, the largest number, has to be the hypotenuse. So if I give you a random triangle and I tell you that two sides are 3 and 4, that means nothing unless, of course, 3 and 4 are the legs. If 3 and 4 are a leg and a hypotenuse, you got to go with the Pythagorean theorem to figure out the missing side. But if 3 and 4 are the legs, then the hypotenuse has to be 5. So if you see these sets of numbers popping up, or you see 2 of these sets of numbers popping up, ask yourself, is this one of the triples that I was supposed to memorize? Because if it is, this problem just got a whole lot easier. Now, if you don't memorize the triples, I'm not saying that anything's going to be impossible. I'm just saying that you're shooting yourself in the foot. Because what could have been a super easy problem, you now have to pull out paper and pencil in order to figure out the answer. So let's start with a little dose of geometry, but nothing too crazy. Let's just figure out some trig functions. Find the value of all 6 trig functions. Remember, when I say all 6, I'm talking about sine, cosine, tangent, cosecant, secant, and cotangent. Now, there's no rule that says they have to be in that particular order. That's simply the order that I memorized them when I was young, so that's the order that I always give them in. It's just like the alphabet. There's no reason A has to come before B, but it's convenient to help us memorize it. So let's look at this one together, show you how it's done, and then you can try the next one on your own. So since I am looking for trig functions, I am eventually going to need to know all 3 sides of the triangle. So let's start with the Pythagorean theorem. I've got 6 and 8, which are multiples of 3 and 4. So the first thing I might think to myself is, hey, is this a 3, 4, 5 right triangle? Because 6 is just 3 times 2, 8 is just 4 times 2, so then 5 times 2 would be 10. So is the third side 10? And of course, no, the third side is not 10. If the 8 was down here, then I would say yes, 6, 8, 10. But 8 is the hypotenuse, 8 is the largest side, so the missing side couldn't possibly be 10, which means let's just use the Pythagorean theorem to find out what's missing. And again, you're more than welcome to write out a squared plus b squared equals c squared, plug in 6 and 8, and solve for the missing side. I'm just going to go straight for it by using my square root formula. I am looking for a missing leg, therefore I'm going to subtract, and it's always going to be the hypotenuse minus the other leg. So 8 squared minus 6 squared. 8 squared being 64, 6 squared being 36, 64 minus 36 is 28, so my missing side is square root of 28. Now, we've talked about this before. Roots do not have to be simplified. I am not ever going to require that you simplify a root. But because half of our test is going to be multiple choice, you still need to be familiar with simplifying roots. That's not a concept that you're allowed to forget. You still have to be familiar with it, but you're not required to do it when it's a free response question. So square root of 28, let's simplify that. What perfect square goes into 28? Well, 4 goes into 28. 4 times 7 is 28. So square root of 4 times square root of 7 really means 2 root 7. So my missing side is 2 root 7. Again, if you still have trouble with simplifying radicals, simply go into YouTube, type out simplifying radicals or simplest radical form, or when it comes to fractions, rationalizing denominators. That is a skill that you should be familiar with all the way back to Algebra 1. My expectation is that you're still familiar with it and you are confident with it. If you are not, you need to go back and do some studying on your own. So I've got all three sides of the triangle. Let's set up our 6 trig ratios, starting with the easy ones, sine, cosine, and tangent. Sine, remember, is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Now it's important to remember when I say opposite and adjacent, I'm referring to opposite of the given angle, theta, adjacent to the given angle, theta. So if theta is down here, that means 6 would be the opposite side, 2 root 7 would be the adjacent side, and of course 8 is the hypotenuse. So if sine is opposite over hypotenuse, sine would have to be 6 over 8. If you want to, you can reduce it to 3 over 4. I am not requiring you to reduce it to 3 over 4, but of course you need to know that it's equivalent to 3 over 4. Cosine is adjacent over hypotenuse, so adjacent would be 2 root 7 over hypotenuse 8. 2 root 7 over 8. There is the ratio. That is your answer, but of course you could simplify it to root 7 over 4. And then tangent is opposite over adjacent, so that would be 6 over 2 root 7. Again, this is an answer, but it could be simplified. 6 over 2 reduces to 3. And then that root in the denominator, it hasn't really come up so far this year, but now is a great time to talk about it. When it comes to simplifying, for some strange reason, some guy years ago decided that you cannot call a fraction simplified if there is a root in the denominator. I have no clue why this arbitrary decision was made, but it was, and thus our job is a little bit harder. So in the event that a root is in the denominator, we have to quote-unquote rationalize it. So again, if you're not familiar with this technique, YouTube, Google search rationalizing denominators. There'll be a whole lesson. You can find a whole lesson about this topic. But good news is it's not difficult. If we want to rationalize the denominator, all we have to do is multiply the top and bottom by that radical itself. So if I multiply the top by root 7 and the bottom by root 7, on the top I would end up with 3 root 7. On the bottom I would have root 7 times root 7, which of course is root 49, which of course is just 7. So 3 root 7 over 7 would be the final answer. If that's the case, let's just do this the easy way. Where's the root supposed to be? On the top, you say? Well, then let's just move the root to the top. We're not allowed to have a root on the bottom, you say? Well, then let's just erase the root symbol on the bottom. So we get 3 root 7 over 7. Anytime you have a root in the bottom, just move it to the top, erase the root on the bottom, done. Rationalized. Again, you don't have to do this. This is an answer, but so are these two. This would be the fully simplified version of the answer. This would be the unsimplified version of the answer. But of course, we're not done. We were asked for 6 trig ratios. Here are the first 3, sine, cosine, and tangent. Good news, to get the other 3, let's just take the reciprocals. If I know sine, then cosecant is just this flipped upside down. Secant would be this flipped upside down. Cotangent would be this flipped upside down. So let's do that. 3 over 4 becomes 4 over 3. Root 7 over 4 becomes 4 over root 7. Of course, we can rationalize that by moving the root to the top. For cotangent, we think back to tangent, which was originally, let's actually go back, 6 over 2 root 7, which became 3 over root 7, which became 3 root 7 over 7. Flip it upside down, but instead of flipping this upside down and then having to re-rationalize it, let's simply just flip this upside down. 3 over root 7 flipped upside down to become cotangent is done. You don't have to re-rationalize anything. So root 7 over 3. And again, that's all you have to do. I'm not asking you to figure out what the angle is. We're going to do that a little bit later. In this set of examples, all we're doing is setting up the trig ratios. So by setting up the trig ratios, we can then later on in the lesson figure out what the angle would actually have to be. So here's another one for you to try. Do this one on your own. Hit play when you're ready. All right, so once again, we're trying to figure out the value of the 6 trig functions. First thing I got to do is figure out what that missing side is, the hypotenuse in this case. And hopefully you noticed 5 and 12, oh my gosh, this was one of those that I asked you to memorize. 5, 12, the 2 legs, go along with the third side, 5, 12, 13. If you remember the Pythagorean triple, then you can simply say, okay, hypotenuse is 13, moving on. If you don't memorize the Pythagorean triple, then this problem becomes a little bit more challenging, not significantly, but a little bit more. Now I have to use the Pythagorean theorem, 5 squared plus 12 squared. 5 squared is 25, 12 squared is 144, add it together, I get 169, take the square root, we get 13. But of course, did you know that the square root of 169 was 13? I do, because I have the first 20 perfect squares memorized, but if you don't have them memorized, now it becomes a problem where you have to go grab a calculator. But what if you're not allowed to have a calculator? Now you're going to have to figure out the square root of 169 all on your own. Wouldn't this have been much easier had you just memorized 5, 12, 13? So please memorize your Pythagorean triples. 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25. I promise you, I wrote the test. I know what's going to be on it. Those will come up. So let's just go one by one, setting up our trig ratios. This one's going to be a little bit easier because there's no roots in there. So sine would be opposite over hypotenuse. We have to figure out which side is opposite and which side is adjacent. If the angle's up here, 12 would be opposite, 5 would be adjacent. So 12 over 13, 5 over 13, 12 over 5. Take these three, flip them upside down for cosecant, secant, and cotangent. 13 over 12, 13 over 5, 5 over 12. All right, let's do the same thing but slightly differently. Instead of asking for all 6, I'm only asking for these 3 trig ratios. And instead of giving you a triangle, I'm simply telling you that the sine ratio is 2/3. What are the others? Now here's a situation where there's a couple ways to figure out the answer. One option is your identities. For example, I know that sine and cosecant are reciprocals of each other. So if sine is 2/3, we automatically know what the cosecant is. It's 3/2. I also know that there's a relationship between sine, cosine, and tangent. In other words, as soon as I figure out what cosine is, I can simply take 2/3, divide by the cosine ratio, and that gives me my tangent ratio. But that still kind of leaves me in a spot because I don't know what the cosine ratio is. Well, an easy way to figure out the cosine ratio is to simply build a triangle. Build a triangle whose sine ratio is 2/3. Well, if the sine ratio is 2/3 and sine is opposite over hypotenuse, that tells me that the opposite side could be 2 when the hypotenuse could be 3. Now, of course, it doesn't have to be 2 and 3. It could be 4 and 6. It could be 12 and 18. It could be any fraction that reduces to 2 over 3. But if the opposite side is 2 and the hypotenuse is 3, I can now use the Pythagorean theorem to figure out the adjacent side. So if I use the Pythagorean theorem, I get square root of 5, and that allows me to figure out what the cosine ratio is and the tangent ratio. So in other words, if you're not given a triangle, build a triangle. Use the information that you're given to build a triangle, and then use the triangle to figure out what you're asked. So cosine is adjacent over hypotenuse, so that would be root 5 over 3. Cosecant, we don't even need to look at the triangle. We know that's 3 over 2. And then tangent, you could either do as 2/3 over root 5/3, canceling out the thirds, it would be just 2 over root 5. Or we can look at the triangle, opposite over adjacent, 2 over root 5, which rationalizes to 2 root 5 over 5. All right, here's another one for you to try. Hit play when you're ready. All right, secant of theta is 17 over 8. We can do this a few different ways, using identities or just breaking down and building a triangle. And of course, building a triangle is going to be the best option until we get a lot more identities under our belt. So let's build a triangle whose secant is 17 over 8. Secant, hopefully you have memorized, is hypotenuse over adjacent. So the hypotenuse would be 17, the adjacent side would be 8. Let's figure out the third side using the Pythagorean theorem, unless, of course, you did what I told you to do and memorized your Pythagorean triples. 8 and 17 are 2/3 of the Pythagorean triple 8, 15, 17. So as soon as I see 8 and 17, where 17 is the hypotenuse, I know the missing side is 15, and we can jump into the problem. So sine would be opposite over hypotenuse, 15 over 17. Cosecant, let's just take the sine and flip it upside down and be done with it. Cotangent, remember tangent is opposite over adjacent, so cotangent is adjacent over opposite, 8 over 15. All right, let's do one more, and then before we move on, once you give this one a try, think about this one before you just hit play and see what I do. So, if you had problems with this one, it was probably because you saw cotangent equals 5 and you didn't quite understand what to do with that 5. Remember that trig ratios are always fractions. Therefore, 5 has to be read as a fraction. And if 5 is a fraction, well, then it must be 5 over 1. Cotangent is 5 over 1. Cotangent is adjacent over opposite, so the adjacent side is 5, the opposite side is 1. This is not a Pythagorean triple. Pythagorean theorem would tell us the missing side is root 26. So let's just look at the triangle to answer our questions. Cosine is adjacent over hypotenuse, 5 over root 26, or 5 root 26 over 26. Cosecant would be root 26 over 1, or just root 26 itself. Secant would be root 26 over 5. Final answer. So now we know how to set up trig ratios, either by when we're given a triangle to use or when we're just giving one ratio to use, and we can build a triangle from that ratio and then use the triangle to set up your ratios. Now let's go that extra step and actually solve the triangle. Solving a triangle simply means finding the missing angle or side. So if there is a missing angle or side, let's use right triangle trigonometry to figure out what that missing angle or side is. As long as you're given 3 pieces of information, remember you've got 3 sides and 3 angles. As long as you're given 3 pieces of information, you can figure out the other 3 pieces of information using trigonometry. Now, in this chapter, chapter 4, we're sticking with right triangle trigonometry. Therefore, one of the 3 pieces of information you're always going to be given is a right angle. So if you're given a right angle, now we could say, hey, we can figure out this missing side using the Pythagorean theorem. We can figure out this missing angle using either sine, cosine, or tangent. And then we could figure out the third missing angle simply by subtracting from 180. Of course, you'd have to know this angle first, and then subtract from 180 to figure out this angle. In Chapter 5, we're going to talk about solving triangles that are not right triangles, but for now, we're sticking with right triangle trig. So, step 1 is to make a decision. Based on the information that we're given, do you want to use a sine ratio, a cosine ratio, or a tangent ratio? Now, of course, secant, cosecant, and cotangent are also available to us. But these are generally calculator-related questions. FYI, make sure you have a calculator handy. And on your calculator, you only have 3 trig buttons: sine, cosine, and tangent. There's no reason to use secant, cosecant, and cotangent because those buttons don't appear on your calculator. So might as well stick to the tools that you have available to us. So I'm going to look at the angle. I'm going to look where are the other 2 pieces of information. I have a 5 on the opposite side. I have a 12 on the hypotenuse. Well, since I have information for the opposite and the hypotenuse, opposite and hypotenuse, opposite over hypotenuse is a sine ratio. So let's set up a sine ratio to help us figure out the answer. And of course, that sine ratio for theta would be 5 over 12. So step 1 of the problem, essentially what we were doing in the last set of examples, was to simply set up a trig ratio. And that's what we've done right here. Sine of theta equals 5 over 12. But we're not done. This question actually asks us to solve the triangle. In other words, we want to solve for the missing angle. I want to figure out what angle has a sine ratio that is 5 over 12. So let's switch our brains into solving equation modes. Theta represents our x. Theta is our unknown. We need to get our unknown by itself. Right now, theta is hanging out with the sine function. Now remember, to get rid of something, we need to use its inverse operation. Now I'm not going to get rid of sine simply by dividing both sides by the letters sin. That makes no sense. Division is the inverse of multiplication. This is not sine times theta. This is sine of theta. Just like if it said a logarithm of x, we would have to use the inverse operation to get rid of a logarithm. We have to use the inverse operation to get rid of sine. Well, at this point, we have not yet defined our inverse function for sine, and I'm going to do that right now. It's called inverse sine. Just like the inverse for cosine is inverse cosine. The inverse for tangent is inverse tangent. We're going to talk about those inverse functions in lesson 5 of this chapter. Basically, at a month and a half from now, we're going to talk about those inverse functions in detail. For now, we simply need to know that the inverse functions of sine, cosine, and tangent are called inverse sine, inverse cosine, inverse tangent. We already know to get rid of a function, we use its inverse function, so let's do that. I'm going to take the inverse sine of both sides of the function because that's how we solve equations. On the left side, inverse sine and sine cancel each other out because we know that inverse functions cancel each other out. So we're left with inverse sine of 5 over 12. That would be the exact solution. But often the exact solution is not sufficient. Sometimes we want to approximate. So that's what we're going to do. We're going to type this into our calculator and approximate. Now, of course, depending on which calculator you're using, it may not look exactly the same, but if you're using any of the TI series of calculators or most scientific or graphing calculators, you're going to have 3 buttons, sine, cosine, and tangent, somewhere on your calculator. And any well-designed calculator, right above sine, cosine, and tangent will have sine to the -1, cosine to the -1, tangent to the -1. Those are not sine to the -1, cosine to the -1, tangent to the -1. Remember, when you have a function raised to the -1, that does not say -1. That is simply a symbol meaning inverse or inverse function. So that is the inverse sine, the inverse cosine, and the inverse tangent. So instead of typing in sine of 5 over 12, I will hit second sine of 5 over 12. And I'm going to get my answer. But this answer is actually incorrect. The correct answer is 24.624 degrees. There's one more thing we need to talk about before we're actually ready to talk about it. All right, and that's how we measure angles. The answer here, 24.624 degrees, is in degrees. The unit is in degrees. But by default, mathematicians don't think in degrees. We think in something called a radian. We're going to talk about radians versus degrees in the next lesson. So for now, what I need you to do is hit the mode button on your calculator. Again, if you're not using a TI series, I have no idea how to do this. Figure it out. But if you are using a TI series, just hit the mode button. On this one, the third line says radian, degree. Right now, the calculator by default is in radian mode. We have to switch it over to degree mode if we expect to get the right answer in degrees. So I've switched it over to degrees, hit enter once, and look at that, 24.624. Again, it's a degree, so I put the degree symbol to say that it's a degree. If you don't write the degree symbol, I'm going to assume that you're talking about radians, and this is absolutely wrong if the answer is in radians. The answer in radians is 0.429. So make sure, this is one of the rare occasions where I actually care about the unit, use the unit. When we're talking about feet versus inches versus yards, I really don't care. The context of the problem takes care of it. But in these specific problems, if it's a degree, make sure you write the degree symbol, because we're going to have 2 different types of measurements when it comes to angles, and you don't want me to assume one when you mean the other. So final answer, 24.624 degrees. All right, here are 3 more problems for you to try. Why don't you give these a try on your own? Hit play when you are ready. All right, let's look at the first one. I first need to decide which trig ratio I want to use. Here is my angle. This would be the opposite side, the adjacent side, the hypotenuse. Since I have the adjacent and the hypotenuse, I will use a cosine ratio. And of course, that would be the cosine of 8 over 15. So I need to get theta by itself. I get theta by itself simply by moving the cosine to the other side as its inverse. Inverse cosine of 8 over 15, type it in the calculator. Inverse cosine, 8 over 15. And as long as I'm still in degree mode, I get 57.769 degrees. All right, here's the next one. Now, this time, notice we're not looking for an angle, we're looking for a side. Now, of course, you did this in geometry. Hopefully you remember how to do this. Or you watched that introductory video at the very beginning of the lesson, so you already know how to do this. Go ahead and give this a try on your own. If you're stuck, though, feel free to hit play and we'll run through it together. All right, so we're going to start this one off the same way. We need to decide which trig ratio we want to use. Now, I don't have 2 sides to work with. I just have one side and the side that I'm looking for. But we're going to think of it the same way. This is the hypotenuse I'm looking for. This is the adjacent side to the angle. Adjacent and hypotenuse still means cosine. But it's not cosine of some unknown angle. It's cosine of 39 degrees. I know the angle I'm looking for. And then cosine is adjacent over hypotenuse, so it's still going to be 23 over x, adjacent over hypotenuse. So this time the x is down here, so we're going to solve for x using our normal algebraic techniques. What's helpful to remember is that cosine of 39 is technically over 1. So this is just a proportion. A over b equals c over d. We worked with some problems in the last chapter that were formatted like this, and we learned one of our techniques for solving proportions is to simply switch the corners. Now the x is in the bottom. I prefer the x to be on top, so what I'm going to do is I'm going to go ahead and switch these 2 corners, move the x to the upper left, the cosine of 39 to the bottom right. X will be on top. X over 1 will be redundant, so I'll just leave it as x. And thus, we've solved for x. Instead of actually cross-multiplying and solving for x in 2 steps, we can simply switch the corners and solve for x in 1 step. So here is our solution. Here's our exact solution. Type it in the calculator. You should get 29.595. Remember that this time we're not using the inverse cosine button. We're using the regular cosine button. I'll type this in: 23 divided by cosine 39, enter. All right, here's one more for you. Try this one on your own. All right, so here's our angle. We're looking for the opposite side. We have the adjacent side, so that tells me I want a tangent ratio. So tangent of 66 equals x over 50. We'll solve for x simply by multiplying both sides by 50. No switching corners necessary on this one, as x is on top. If x is on top, just move the denominator to the other side. So 50 times tangent of 66, type it in the calculator. I get 112.301.